Okay, good afternoon, everyone. So we're going to start a new unit today. I think we'll be able to cover it pretty quickly in just 2 lectures. So we'll have today and then next week. But this is fun because it takes a very different perspective on machine learning, some really new ideas. So, and there's basically 2 sort of different ideas in this unit, ensemble methods and decision trees. And then there's also interesting things happen when you put those 2 ideas together. So let's start with ensemble methods. So imagine that you have a biased coin, a coin that when you flip it turns up on one side more often than another side. And your goal is that you want to determine which of the 2 sides is heaviest. And although you don't know that this is the case, let's say that heads occurs 70% of the time and tails 30% of the time. So if you wanted to figure out which of these 2 sides is heavier, you could imagine flipping it. And if you flip it once, and whatever side comes up, you say that must be the heaviest side, you would be correct 70% of the time, right? Because that's the probability that that heavy side comes up. Now, if you would have flipped it 11 times and then chosen the majority vote out of those 11 times, turns out you would be correct 92% of the time. And if you repeat this for more and more coin flips with majority voting, by the time you get to 31 flips, you're correct 99% of the time. So these numbers come from the CDF of the binomial distribution. And what you can see here is that as you use more independent trials of this random coin flip, your prediction improves. So then you might say, well, what's the relevance to classification? Well, what if we have 31 binary classifiers, and each of them is pretty weak in that they're only correct 70% of the time. So if I just use one of them, that's a pretty weak classification. But maybe we can use a majority vote of those classifiers, and according to this table, we'd be correct with 99% accuracy. So this is how we'd like to use this idea for machine learning. But the key caveat that we've assumed up here, that we're assuming again down here, is that these classifiers are generating statistically independent outcomes. Obviously, if the classifier is always giving you exactly the same outcome, it doesn't matter whether you do it once or 31 times, it's always the same. And so the more diverse or the more independent those outcomes are, the more gain you get from averaging them. And that's what we see happening here. So in the context of learning, we call these individual, weak predictors, we call them weak learners. We call the combined one a strong learner. And we call this process of combining them ensembling. Just some terminology. So, any questions on this kind of main idea? Okay. So the key question then is, how do you get statistically independent outcomes or something close to that out of different classifiers? So I guess, okay, but we're going to get to that in a moment. But let's just talk about how we implement the method we talked about on the previous page. So there's a couple versions of this. The one we discussed on the previous page is called the hard voting classifier. And that would just take the majority vote of hard decisions. But there's something a little bit better than you can do. If your classifiers give you soft outputs, which means, if they're binary, that means they give you a probability. Or if If there's more than two categories, then they would give you a PMF over the different classes. In either case, what you can do is you can just average those soft outputs, those PMFs, first before choosing the maximizing class. So that's going to work a little bit better than basically maximizing first and then doing the majority. Okay, but both of those options are available in this scikit-learn voting classifier. And again, the main idea is that this should improve your performance if the base classifiers are sufficiently diverse. So the question then is how do we get diverse ensembles of classifiers? Okay, and there's basically sort of two methods or two overall strategies. You could imagine training a common prediction model using different data sets. So, maybe you want to use a neural network, but you train it with different data sets. Now you're going to have different weights, and they're going to behave differently, and they might give you some different diversity. Another idea is you use a common data set for training all models, but you use different prediction models. So maybe you train one logistic regression, another SVM, another neural net, and then you average their outcomes, you ensemble their outcomes. Another version of this last one is common data set and even a common model, for example, logistic regression, but what I do is I give different subsets of features to the different models. So one of my logistic regression gets half the features, and another regressor gets the other half the features. So different models, different features, different data sets. And then there's another thing you can do is even if you have the same model and the same features in the same data set, you can, when you train that model, you can use different weightings on the loss term. And we'll see a version of this called boosting, not today, but next week. Okay. And though everything we said here corresponds to classifiers, all these ideas are also possible with regressors. Of course, you don't need to, the hard voting not, but the rest of the ideas work for regressors too. Okay, so we'll dig into some more of the details of this stuff in the coming pages. Any questions so far? Okay, so let's look about how we can get data diversity. So there's two main methods to do this. The first is called pasting, and that is drawing training samples without replacement. So for example, if you have two different models, it means you take some fraction of the training samples, maybe you draw them randomly, give them to one model, and then whatever remaining training samples are, you give them to the other model. Okay. But there's another version that works a bit better than this called bootstrap aggregating or bagging, which is where you draw the training samples with replacement, meaning that let's say I draw a set of samples, let's say I draw a single sample for one model. Well, next time I draw a sample for the same model, I don't remove that sample from my training set. I might actually draw the same sample again. So every time I go to draw a sample for a model, I consider all the samples. Okay, so at the end of the day, for each model, a sample could be used several times, and some samples might never be used. So anyway, this method is quite famous in statistics, and it's been analyzed a lot, and it works really well. A little bit more on bagging is what's typical is if you have n total training samples, then what you do is you draw n samples for each predictor. And if n is a large number, you can show that approximately 1 over e, or 37% of your samples will go unused for each predictor. So 37% will be redundant, and 37% will be unused. But the nice thing about those unused samples, you're not using them for training, you can use them for cross-validation. They're called the out-of-bag samples. So they're not entirely wasted. Okay, so that's the idea behind bagging. Any questions? Yes?
Does the size of n depends on which one of these passing or bagging better for?
So again, n is the total number of training samples, just like always. So when you do bagging, you have a choice for how many training samples you use. And I'm saying you typically use n per predictor, right? Now for pasting, n is the total number of training samples that is shared across all predictors. So if you have, L predictors, they each get n over L samples. So you don't have such a choice there. Okay. And so these are available in scikit-learn's bagging classifier, bagging regressor. And with the bootstrap parameter, you can control bagging versus pasting. And with this out-of-bag score, you can have it report the out-of-bag cross-validation. Yes?
So what makes bagging work better than pasting?
Well, I think some of the intuition is that, if you want to average a lot of predictors, which here, based on this intuition, it seems like we want to average, maybe not just 2, but maybe a bunch of predictors. Let's say I want to average 10 predictors, right? Well, if I use pasting, that means that their training sets will be 1/10, which is much smaller than the samples I have. But when I do bagging, I'm going to be using about 63% of the training samples for every predictor. So that might give some intuition about each of those predictors will be stronger. Now, they're going to be less diverse than the pasting ones, but maybe that's made up for by the fact that they're individually stronger. Okay. Great. Okay. Any other questions? Okay. So that's how we can sort of inject randomness from training samples. We also said you can inject randomness by giving different subsets of features to different predictors. This is most useful when there's many features, large D, and those features are correlated. If you just have a few features, you can't really distribute your features very well across predictors because the predictors won't work well. But if you have many features, and especially if those features are correlated, then that means that you should be able to do reasonably well with subsets of those features. And in terms of splitting the features up over your models, you can do, again, sampling with replacement or without. So you can do this bootstrap idea across features, also. And then you can combine the random subsets of features with the random subsets of training data. If you do both random data and random features, they call that random patches. And if you do random features but full data, random subspaces. So this is all just some terminology, probably from the statistics literature. And yeah, so this is all done in bagging classifier and bagging regressor. You can randomize the features as well as the data samples, training samples itself. Okay. All right. So those are just some things we can do for ensembling. Many options. And you're welcome to play with these ideas in the final project too. Okay. Any questions? All right. So now we're going to switch gears, talk about something different. We talk about decision trees. And these are very general. We can do regression or classification with them. They're also called classification and regression trees, CARTs. So different terms for this. In scikit-learn, they use decision trees, so that's what I'll use. So basically the setup, the training data is the same we've had all semester, so we have some d-dimensional features. We have some labels. The labels could be real numbers, they could be categorical. Either one we can handle with this approach. And the main idea is also pretty simple to describe. We partition our feature domain into capital L different regions. So for example, this would be a two-dimensional features. Here I'm splitting this up into 1, 2, 3, 4, 5 different regions. And then for each region, whenever your test feature lands in anywhere in this region, R2, you output the same value. So this is a picture of that. So here we're showing the features, and then we're also showing the prediction, which here is called Z. And so you can see anytime you're in this region here, which is down here, you are outputting that same value. And anytime you're over here, you're outputting that value. And if the regions are given to you, it's pretty easy to see what a reasonable value to report would be. So if you're doing regression, you could set the value within this region as the sample mean of all the training samples that landed in that same region. On the other hand, if you're doing classification, you can't do averages over categories, but what you could do is you could look at all the labels that landed in this region, and you could look at the most commonly occurring one, which is called the sample mode. So if someone gave you the regions, then it's relatively easy to figure out what values you should report. Determining the regions is a little bit more complicated, and we'll talk about that next. But is the overall idea kind of clear, what they're doing? Okay, any questions? Okay. Okay, so why are they called trees? Well, the way they're constructed is by recursively partitioning the feature space. And so what I mean is you split the feature space in half. And then in those two halves, you split them in half. And then you keep splitting and splitting down to smaller and smaller regions. And the way that you do the splitting is thresholding a single feature. So for example, here's a depiction of the tree. Let's say we decide to split feature x1 first, and we'll assume this is an ordinal quantity. So let's say we have a threshold t1 in mind. And so here you can see at the very top of the tree, we decide it's either on this side of the threshold or on this side of the threshold. And that shows which way we go down the tree. Now let's suppose that the sample is on the left side of this. So then the next decision says, okay, is x2 less than t2? So if so, you go on that, less than t2. If so, you go on this side, otherwise you go on this side. So that's how you can create these two regions. And then the regions on the right are done in a similar manner by splitting, in this case, x1 and then x2 according to some new thresholds. And at the end of the day, you have 5 different regions here. So that's the idea. The decision regions are basically the leaves of the tree, and the entire domain of your features is the root of the tree. Okay. And so because we're thresholding a single feature at a time, that means our decision boundaries are always parallel to the coordinate axes. So we can't get, weird boundaries like this if we do this thresholding a single feature at a time. So that, although it restricts the kind of boundaries we can make, it's still, I guess it's done because it's very convenient. At every stage, you can just consider a scalar. Any questions? Yes?
So these 5 regions are like output number of classes, like
No. So let's say that let's say we're doing binary classification, and so there's going to be two possible labels, right? So what you would do is, for each region, you would report one of those two possibilities. And so the picture would look a little different than this. There would only be, maybe a 0 and a 1. But you could have, like, this could be 0, this could be 0, and then maybe all the other ones are 1.
And deciding that based on considering the features x1, x2.
That's right. And in this case, there's two real valued features here. Yes, right. And so the number of regions that you make is sort of like a bias variance trade-off thing, right? If I want to do perfect classification on my training set, that's easy. I just keep going until each region has a single training sample in it. And then now everything's classified perfectly. But obviously there could be overfitting, because when I put my test sample in there, it may not land in the right region, right? So so the number of regions is a bias variance sort of question that we have.
And this is in terms of classification. What about regression?
So this picture would be for regression. So in regression, even though the output is continuous, when we have 5 regions, we're only able to output five different values. Right? That's just by design of the tree. There's only 5 leaves of the tree, and we output the same value, anytime it gets to that leaf. So there's a sort of quantization in terms of what we can report, but that's how trees work. But even there, if we make enough regions, we can assign, so that I have a single training sample in each leaf, then I can perfectly assign the number and I can get 0 training error. Okay, all right. Good. So is this making sense? Any questions? Okay. So, so let's talk about how we train them then. So we do this in what's called a top-down manner, where we start with our entire training set, all n samples, and we initialize this index set that we'll call S, and that's just going to contain the indices of all our training samples, 1 through n. And what we're going to do is we're going to do this recursive partitioning. So we're going to split S into 2 subsets, S1 and S2. And so we can think about, basically where some subset of the training indices will land in S1 and the remainder will land in S2. And the criteria that we're going to use is that the labels are most homogeneous or similar within each subset. So that is the guiding wisdom of building the tree, training the tree. So we'll talk in detail about homogeneity metrics, but basically if we're talking about regression, then you want that all the training labels are as close as possible within each one of these subsets. And same thing with classification, with categories. Okay, so how do we make this decision then about the splitting? So what we do is we consider some feature J. Maybe we start with the first feature, and we consider some split T. And these are both hypothesized. We hypothesize a certain pair of J and T. And so for all the training samples, Xij, that are less than T, we put those in S1, and for all the training samples that are greater than T, we put them in the other subset. So that would be if this was an ordinal feature. Now if we have a categorical feature, we can't really compare to a threshold, but what we would do then is we would just consider all possibilities of how we can split up those categories. So if we have 4 categories, A, B, C, D, you can imagine there's a bunch of different ways to form subsets out of those four things. This is just one subset. I could form AC and BD, but there's many other ways I could form subsets. Okay, so the point is that for every feature, you sort of consider all possible thresholds or all possible categories. Now, if you think about this, all possible thresholds, does that really mean you have to consider an uncountably infinite number of variables, possibilities for t, or not? What do you think? Let's say I have this one feature x. I have 10 training samples. How many different thresholds do I really need to consider? Just 9, right? Because maybe I'll do it like this. So let's say I have, this is my n equals, I'll just do 4. I have 4 training values, and I'm saying, how do I split this into, what thresholds do I need to consider? Well, this is one possibility for my threshold. Another possibility is the threshold is here. And notice that like any threshold in this region gives me the same outcome, right? So I can just put the threshold right in the middle. So that's 1, 2, 3. Okay. So the number of t I have to consider here is actually finite. And it depends on how many samples I have in the subset S that I'm starting with. Okay. And also the number of subsets of categorical possibilities is also going to be finite. Okay. So basically, what you do is at every split, at least in the most generic framework, you do a joint search over all features and thresholds. So this can take a while. There certainly are tricks. Like we said earlier, maybe we want to do something like give it a random subset of features or things like that. But for now, we're just considering the simplest case where we look over all features and all thresholds. And finally, after doing that, and having some notion of what it means to be homogeneous in mind, we can decide on the split. And once we've split S1 and S into S1 and S2, then we look at them individually and we split them further and so on. Okay, and when do you stop? Well, one reason to stop would be the labels are the same within every subset, because then there's no way splitting further is going to help you. So that would certainly be the case if you have a classification problem. You might have a bunch of features with the same label. Or in the regression context, you could get there by going all the way to a subset of size 1. And we said you might not want to do that because that could be overfitting. Another thing you could do is you could stop early. You could say, I don't want any of my subsets or my leaves to have less than 10 samples. And so once it gets to 10, you just stop and you don't split anymore. You could also say, I don't want my tree to be more deep than a certain number of layers. And so that would be another reason to stop at some point. So there's all different ways you can decide to stop this process to control things like overfitting. Okay, but that's basically how we do it. Is this making sense? Okay, so let's just do a simple example. So here we have a risk prediction problem, like something from an insurance. So we have these drivers of different ages. They drive these different car types, and they're either low risk or high risk. And this would be our training data. So like some humans have decided on these, and then we want to turn this into an automated process by which a new applicant would be classified as a high or low risk driver. So to make this a little bit easier to parse, let's organize things a little better. Let's say organize by age. So we'll do 17, 20, 23, 32, 43, 68. Okay, so I've just arranged them by age, and then I'll do my high risk or low risk. I think we have high, 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 and then we have low, high, low. Okay, and let's say that we just decide that we're going to start training our tree by using age as the variable, as the feature. So we would like to figure out, how do we split this subset of samples into the most homogeneous two subsets? So for example, I could split here, I could split here, I could split here. You know, for example, if I split here, then this would be one subset, and this would be the other subset. Okay, so let's see. Is Colton right here?
Yep.
Okay, so what do you think is going to give me the most homogeneous subset?
Split between 23 and 32.
Exactly, because even though this is not perfectly homogeneous, this is, and if we split it this way, then this is even less homogeneous, although maybe we need to be specific about how we're measuring it. But you can kind of see that, you know, it's very reasonable to split here. And that's exactly what's done. 27.5 is exactly what's between those two numbers. So here on this side, what's nice is if the age is less than that, we automatically would classify that driver as high risk. Okay, now we have to work on the remainder of the samples. And we can write the car type down as, let's see, truck or sports or family. Okay, so now we need to do a split again, but this is a categorical split. So how can we split these to be as homogeneous as possible? Let me see, is Spond Meta here? Okay, what about Eason He? No. Okay, I don't know, John Zumberger? What about Jun Xie? What about Kyle? I think Kyle is Kyle here? Thought I saw Kyle. Oh, there you are. Yeah.
Could you repeat the question?
Yeah. How do I split these into two most homogeneous subsets? Homogeneous means similar in terms of these labels.
I'm not sure exactly.
Okay, so if it's a sports car, we use that to form one subset, and if it's not, we use that to form the other, and they're totally homogeneous in that all the sports car are high risk and all the non-sports cars are low risk. So that's this splitting here. And at this point, we have there's no reason to split further because all the training labels are identical in each of those leaves of the tree, and we're done. Yes?
If the division between 22 and 32, 23 and 32 wouldn't make a difference on this data set, how are you going to make sure that it's going to predict better for the income data in future? Like, how do you decide which number you actually choose for the age?
So I guess I'm not sure about your question. So what are you, because like we have this procedure here. We haven't yet defined homogeneity. We'll be more specific in the coming slides. But so once you define the criteria by which you're going to measure similarity, homogeneity, then you also have to decide things like your stopping rule. You know, like how deep do you make the tree? You know, you could choose to to only go one depth. And that decision you can make using cross-validation. So you can try different things and cross-validate over those hyperparameters. Does that make sense?
Yeah.
Okay. All right, good. Everybody good on this example? Yes.
Say, for example, the car of the age 17 was low risk. Would that mean that there would be another branch on the left side of that tree to do like a split between 23 and 32 and a split between 17 and 20?
You certainly could, yeah. You could do that. And if your criteria was to go until you couldn't, there's no reason to split further, you would do that. Yes, right. Okay, great. Everybody good? Okay, so now we can be more specific. How do we do this for regression? So we want to maximize homogeneity or similarity within the subsets, or you could minimize inhomogeneity within the subsets. So that's useful because if you think about regression and you think about variance, variance tells you inhomogeneity, right? The larger the variance, the more deviations there are among the samples. So when you do this splitting from S to S1 and S2, what you could do is you could first compute the sample mean in each of your two subsets, and then you could compute the sample variance in each of your two subsets. You know, using that sample mean, we'll call the variance VL for L is 1 or 2. And now you have two variances, so you want to get that down to one number. So it makes sense to look at some averaged variance where you're averaging according to how many samples are in the two subsets. So finally you get this average variance V, and you would choose your splitting to minimize V, minimize the variance within the average variance within the subsets. Does that make sense as a, okay. So that's one option. Another thing you could do is you could look at absolute error, because that is also something, you know, the larger the error, the more dissimilarity there is relative to the mean. And the advantage of this is that it's a bit more robust to outliers than variances. So both of them would be reasonable approaches, and we'll see a much more sophisticated approach when we discuss XGBoost next week. Okay, so that's regression. Any questions on regression? Okay, so what about classification? So let's consider classification where our labels are in one of K different classes. And so what we have to think is for a given subset, we have to look at what I'm going to call the empirical label PMF. So let me just try to draw this. So let's say we're looking at subset 1, so L is 1, and so this maybe, I don't know, I'll do K equals 4, so that means there's 4 possible labels. And so we could have something like, I don't know, here, you know, this would be one example. These are probabilities. And what do we know about PMFs? Well, we know they have to sum to 1, and they have to be non-negative, right? But otherwise, we can have any 4 numbers here that say over those 4 classes K, how is the data distributed within that subset? Okay, so let me erase this. So, okay. So what's the most homogeneous that I could possibly have in terms of that PMF? You want to take a guess? So if I have a bunch of samples in a subset and they have different labels, what's the most similar I could ever get?
If they all have the same classification.
If they all have the same label, exactly. And in what case, what would the empirical PMF look like in that case?
100%.
So what are the 4, like an example of those 4 numbers?
Oh, it would be like 1, 0, 0, 0.
Exactly, right? So something like that or like this, you know, that kind of what we call Kronecker delta or impulse or point mass, that would be the case the most homogeneous. They all have labeled k equals, I don't know, maybe 2 in this case. Okay, what is the opposite? What is the, the most disparate I could have, the most inhomogeneous that I could have in this case? Any guess? Same probabilities, exactly. So that would be something like this. And if I have 4 labels, they would all have probability 1/4. Right, so those are kind of the extremes that we have for classification. And so the most common way to measure this, to boil it down to a number, is something called Gini impurity. And so what the Gini impurity is using this PMF, you form this quantity for each subset L. So here maybe we just have 2 subsets when we're doing the splitting. So we would have 2 PMFs, and we would compute these numbers. And then we would just do this averaging like this, similar to what we did with the variance. So now we can compare these, let's look at these quantities. Okay, in the case that we have, let's look at this case. This is the most inhomogeneous, the least homogeneous. The values, these p's are each 1/k, right? So when we would get 1/k squared if we plug them in, and then we would sum this over k, and this would be 1/k total. Okay, so the biggest you can ever get here is 1 minus 1/k. Now on the other extreme, when we have this impulse type distribution, then we know that there's only one value here that equals 1, and the rest equals 0. So when you sum that up, this whole sum turns into 1, right? Because you're summing up 1 squared plus 0 plus 0 plus 0. And so you get 1 minus 1 or 0 here. Okay. So this metric is just sort of a way to get a number out of this PMF that describes how similar it is. There's other ways to do it, but this is, I think, the most common one, at least for trees. Okay, any questions? Okay, so now we have, for regression and classification, we have a way of doing this. We know exactly how to design our tree. Like in this case, we were kind of guessing as to how to measure inhomogeneity, but we could check for every possible threshold. We could compute the Gini coefficient for those labels and find, what is in fact the best one, and I'm sure it would be this split. Okay, all right, any questions on this? Yes?
So, while making the first split, we considered the age criteria, right? So why didn't we consider the other criteria, or can we do that?
Yeah, I guess, so according to the procedure we've outlined, let's come back. We would really want to do a joint search over all features and thresholds. So that would mean, we hypothesize that it's the age feature. We figure out the best split. That's a hypothesis. And then we go to the card type feature, and we do that. And then we say, okay, no, age was better. That's how we would officially do it. Okay. Good. Any questions? Yes.
Why is the Gini impurity a measure of inhomogeneity? Is it because it's comparing the actual PMF to the average one?
Yeah, it kind of has to do with this quantity here, and I guess it has to do with the fact that these numbers must sum to 1. because it's any PMF must sum to 1. And so if you have something that sums to 1 and you, basically it's like you minimize a square, you either minimize or maximize the square. You go from these extremes of making them all equal or to making it a spike. And that sort of agrees with the extremes of perfectly pure or, the opposite.
It's because if you have an impulse, it will be, the term will be 1.
Exactly. And then you get the smallest value. And then the opposite, you get the largest value. So it's just sort of a way that's consistent with those extremes. And then you get any number in between. Okay. But there's other ways to do it. Entropy, misclassification error, chi-square. We won't get into it, but the details are in these books. Okay, great. Any questions? Okay, so now what if you have a generic loss? Maybe you have binary cross entropy, something like that. You can also use that as well. So to do this, we want to write the tree in a particular way. We'll also use this later. We want to think about it as sort of a two-step process. First, there's a function we'll call Q that takes in your feature vector and assigns it to a leaf. So Q outputs an integer. And then we have ZL, which we talked about. That's just the value assigned to leaf L. So we can think of the overall decision tree as sort of a composition of Q followed by this lookup table Z. And so when we talk about minimizing this loss, we can split the sum over training samples into this double sum. There's the outer sum over the different leaves in the tree, and then the inner sum over all the training samples that land in leaf L. Okay, so this is just a different way of writing this sum, but it allows us to separate the design into the design of this function Q and the design of these outputs Z. Okay, so this is basically the main idea. This is rewritten as this, and then now we can think about how we minimize this using that top-down splitting procedure. Okay, so again, for the top-down splitting procedure, we start with a subset, with a set S or subset S, and we split it into 2. So what that's going to mean is that before the split, this is going to be the loss. So we look at all the samples in our original subset S, and we find the Z1 that minimizes the summed loss. Now, after we do the split, the difference is we're going to get 2 subsets, and we can individually optimize the losses, the Z's in each of the 2 subsets. So for every hypothesis about how to split, we can reevaluate this and eventually choose which split we're going to use. So try all feature threshold pairs, each of which leads to a given split, and then evaluate the loss for each split and finally choose the best one. Does that make sense? It's basically the same idea, but instead of inhomogeneity, we have whatever loss we're starting with. Okay. And this can also give us a stopping rule, because if we do a split and we notice that the loss has not decreased at all, then there's no reason to do the split. You can stop there. Okay. You want me to go over this anymore, or is this good? Okay. Good. So let's do kind of a recap then. Advantages of decision trees. So they're very general. They can handle both ordinal and categorical features. They can even handle many categorical features, which is kind of tough. If you think about doing like one-hot coding, when you have many categorical features or many categories, you have to add like a massive number of those extra features. So things kind of get out of control. Here, complexity is not as much of an issue. You also do not need to standardize the features, because if you shifted or scaled the features, the tree would just adjust and there would basically give you exactly the same predictions. So no need for standardization here. One of the biggest advantages of trees is that they're very interpretable. It's what we call a white box model. You can see exactly how a tree arrives at its prediction. A neural network, right, it does amazing things, but we don't really understand what it's doing. And so actually, for certain industries like insurance, there's laws that say if you, classify a customer in some way, you have to be able to explain why you did that. And so you could not use a neural network to do that, because it's like you can't explain why you came up with the ruling that you did. But if it's a tree model, your tree shows exactly why they were classified as high risk or low risk. Also, the prediction is very fast. If you think about, let's say that when training the tree, just roughly speaking, at every split, you split your data in half. And if you start with n samples, after one split, your subsets are n over 2. After 2 splits, your subsets all have size n over 4. 3 splits, n over 8, and so on. And in log 2 based n depth, you will get to where all the subsets have a single sample left. Right? So that's not exactly how it turns out, but you can say, on the order of L of log 2n decisions, that's how many, that's the depth of a tree at most. And so you can see that even if you have a large training set, you actually get through your tree pretty quickly. Okay, disadvantages. Training can be expensive, especially if you consider every feature for every split. And so what we said is to bring in the ensembling ideas, what if you only choose a few random features for every split? That actually might help with overfitting. And that will speed up the training your tree. Overfitting definitely can be an issue with trees. We saw that you can fit perfectly to any training data set if you have enough depth. But that's not necessarily what we want. And like an interesting observation is that if you train a tree with one data set and then you take out one sample from the data set and train another tree, taking out that one sample might change the entire tree. It's just something that can happen. And so you can see how these trees are highly dependent on the data, how they can overfit. So the techniques to deal with this is things like enforce a minimum number of samples per subset, never make the subsets too small, only allow the tree to go to a maximum depth, and so on. There's a good overview of this in scikit-learn. Okay, so the last idea, which is very simple to explain, is just have one slide, is random forests, which is a very successful approach. We know that these decision trees on their own, they tend to overfit. It's easy to make them have very low bias and high variance. So what you can do is you can use a random collection of many trees called a random forest. And what you do is you use a random subset of your data to train each tree. You could do bagging or pasting. And within each tree, consider a random subset of features at each split. And so then you can train all these trees in parallel. And you can also do inference in parallel, and you just average the results that come out of the trees. And you can take even very crude trees, like trees with depth 1, called stumps. And if you have enough of them, you can get a really good prediction. So this is a little picture showing trees that on their own are pretty crude. They're coming up with kind of strange decision regions. This is a classification problem, as you can see. This is sort of like 2 moons of data here. And individually, the trees are doing weird things with very small decision regions, but they're doing them in different ways. And finally, when you average them, you get a decision region that looks pretty sensible. So here there definitely are a number of different hyperparameters to adjust, like how many trees, what depth to use, other things. And those are parameters you can tweak and play with if you do this with your final project. But random forests are a very powerful and general method and usually work quite well. Okay, so that's, any questions on random forests or decision trees? Great, okay. So that is basically half the unit, and we'll cover the other half after the midterm. See you guys for the midterm on Friday.